I want you to imagine I have any randomly shaped chunk of conductor in space. So again, since electrons are free to move, if you place a conductor inside an area of space that has a strong external electric field, the charges will move around and separate so that they will cancel out the field inside the conductor, making the electric field inside the conductor always zero. Invariably, some student every year asks, well, can you have a strong enough electric field to overcome this power and force there to be an electric field inside the conductor? No, you can't. It doesn't work that way. The electric field will always be zero. There's always enough charges. Now, this ends up having some interesting implications and generates for us a couple of interesting discussions. Now, before I get too deep into that, let's have let's go with something square, a square conductor that is hollow on the inside. If you apply electric field outside the conductor, what do you think the charges are going to do? Now, I know there's no conductor in here, and we know the electric field inside the conducting portion has to be zero. But even in this region of space, the external electric field will be zero because of the movement of those charged particles. Charged particles are going to separate so that all the electrons are over on this edge. It's going to reveal positives on this edge. And that will make the electric field even inside the cavity zero. So you have to listen for this, but there's a charged conductor and there's a charge conducting shell. But they'll both produce an electric field of zero inside. So whether it's a solid conductor or a conducting shell, you get an electric field of zero inside the conductor. Now this room isn't a conducting shell. It's made mostly of cement. But this is where I want to start. This is a good place to start. And there's two different versions of this question. We're going to be doing the version that's mostly focused on the electric field. There's a version that's mostly focused on the electric potential. And what I want you to do is pretty simple. I'm going to ask for two questions. I'm asking you two questions. I want the electric field. What we're looking for is a function for the electric field as a function of displacement from the center. And so what we're really looking for is an electric field where R is less than A, an electric field where R is between A and B, and an electric field where R is greater than B. Can you see that those are kind of the three regions of space that would make sense? So we're asking for electric field here, here, and here. The next thing that's almost always asked in relationship to this is the surface charge density. And that would be the surface charge density at A, the inside of the sphere, and at B, the outside of the sphere. Super common question. And then, of course, plot the E field. Now, Gauss's law is going to do this problem, and there's really not that much to do here, as you have done Gauss's law before. So consider the first problem. Let's do Gauss's law. Let's deal with R is less than A. So I'll put a Gaussian sphere on the inside of my of my conducting shell. I don't think I have to do a whole lot here. Can we skip through all the steps that we did for Gauss's law because we've done the point charge already, and recognize that the flux is going to have to be equal to E times 4 pi r squared? Or do we need to go through the whole set of steps on how we got that? Guys, you should be honest, because I'm reaching a point where it's probably getting time for us to practice and have a quiz. And then I think a test after this. So do I need to go through the steps? So why don't you show me that you guys took notes? What's step 1 on trying to apply Gauss's law? What's that? Yeah, except we only have a point charge. So I don't think I have to find the charge density. Find the shape of the electric field. That's the first thing. So let's find can we agree that the electric field is going to be radial from this point charge? All right, that's good. So second, find the shape that we're going to use for Gauss's law. That might have been what you were indicating. I think a sphere works because we have spherical symmetry. That good? So starting with the flux, remind that the flux is a summation where I have to add up every bit of electric field and every bit of area that it penetrates and deal with the direction between the electric field and the area. So I write out flux. Let's see if we can exploit the symmetry here. Can we agree that the area will be in the same direction as every bit of electric field? So that deals with the cosine. So that allows me to take this and write this as E times dA, strip away the vector information, and write cosine of 0. Next, can we say that the electric field will be the same size at every point on that sphere because it's the same distance away from the central charge? So I can move E to the outside, cosine 0, and I'm left with doing a summation of the entire area of the sphere. And can we say that the entire area of the sphere is equal to 4 pi r squared? So that's what gets us to that. This one's pretty easy. We didn't have to break our area up into multiple pieces because it's just one area and electric field penetrates all of it. Just kind of repeating what we've talked about, but I like somebody who will request, yes, let's do that. Now, the next side of this is to remember that we have to look at the charge enclosed, and that's just going to be Q. Right? So we've done charge enclosed, we've done flux. So Q enclosed equals epsilon naught times the flux. So Q equals epsilon naught E 4 pi r squared. And then we get, I hope, the obvious answer for the electric field. So electric field for R less than A will be Q over 4 pi epsilon naught r squared. All good? Any questions about that? So our next place to move maybe would be outside the sphere. Is that okay? If I go outside the sphere, what's Q enclosed? Q, it's still the same charge, right? So nothing extra has been added, so Q enclosed is just Q. Now, if the conductor were charged, that'd be different. But we just did a neutral conductor. Flux. Now, here's where you might want to ask, what's happening in the conductor that will make this happen the way we think it might? Because how many of you think the electric field is probably still like spherical, like so? Well, if my charge is positive, does it seem reasonable that electrons are being pulled in towards the center? And that's going to reveal positive charges on the outside? Well, that's happening everywhere around the conductor. So, yeah, we're going to have electric field that seems to be still radial on the outside of my conductor. Therefore, the whole set of steps, the whole doing the E dot dA is going to look exactly the same on the outside of this conductor. So I'm going to just skip down to where I write this as E times 4 pi r squared. Bring these two things together, and the electric field is going to be equal to Q over 4 pi epsilon naught r squared. Now this is for the electric field greater than B. Yep.
So can you like use a conductor to like the strength of an electric field strong over the distance?
No, because it's still over the distance squared, and we're just out here now, so it's almost as though the conductor doesn't exist. Right? It's invisible. Except,
I thought so that r squared for this side's not from the edge of the conductor, it's from the point charge, right?
it's still from the center, yeah. Because it's still based on the size of the sphere, right? This is the area of that sphere, so it's still based on the center.
Gotcha.
All right, so let's put a Gaussian surface in here. What's the flux? Do the same set of steps. Because Q enclosed, still Q, right? So if I do my set of steps to figure out the flux, I'll have the integral of E dot dA. But what's our rules about conductors? E has to be 0, so the flux has to be 0 inside the conductor. Period. There's no calculation here. That means the electric field, when R is greater than A and less than B, is 0. So let's skip down to question 3. We found the electric field. What must the electric field look like? Let's put in stops for A and B. This is the electric field as a function of R. All right, so I'm seeing a lot of interesting things out there. Some of it I'm seeing is makes perfect sense. You notice that this and this one are exactly the same, right? So the truth of our graph is that those two, if the shell wasn't there, I'd have something that looks like this, right? Because this and this produce the same function. Everything about it, every part of the thing that is a constant stays the same between the two. Except we know that between A and B, electric field has to be 0. So that's all you have to do. It's the same inverse square function, except in the space where you are in the conductor, it's suddenly 0. So what they're looking for is they're looking for this point and this point to be at different heights. They're looking for the fact the electric field attenuated because you got further away. So they want to see that there'd be this continuity if it wasn't for the conductor in there. They want to see this abrupt change in the electric field to be 0 for the time that you're in the conductor. They don't care about whether you use the symbols right to show whether there's continuity here. You guys remember all that crap you learned about putting a little circle on the end and the filled-in dot and all that? None of that matters because they're assuming that the abrupt change at the surface of the conductor is already odd, and we don't have to worry about that. So these circles I drew in there were just demonstrative. I don't have to have them, and in fact, I would not put them if I were you. This is what they will want to see as an answer. But there's something else I'd like you to consider. Q enclosed isn't this. I said that from the beginning just because I knew you'd buy into it. But the Q enclosed isn't Q. When we consider the Q enclosed, it has to include all of these negative charges that are on the inside. Do you understand what I'm saying? Q enclosed is actually going to have to be 0. This charge brought in all these negative charges to produce the situation where there was going to be an electric field of 0 inside the sphere. So my Gaussian surface encloses a charge of 0. So how much charge must there be on the inside surface of the conductor? Minus Q. Right? It's the only way I can get a total enclosed charge of 0 is if there's a charge of minus Q on the inner wall. So, let's see if I can clean this up a little bit. So if I have total charge here, Q, on the inner wall, there must be a total charge of negative Q spread out uniformly on the inner wall. That's the only way the sum of the charges will be 0. We've separated charges in the conductor. In fact, for this surface, some of the charges is still Q, but we have separated the charges inside the conductor. So although there's a negative Q on the inside surface of the conductor, what must there be on the outside surface of the conductor? Positive Q. So what is the surface charge density at A? Well, at A is on the inside of the conductor. The surface charge density will be the entire charge on the inner surface of the conductor, minus Q, divided by the surface area of the sphere, 4 pi A squared. This is the surface charge density on the inside edge of the conductor. Remember, density is charge over shape. Again, density is charge over shape. At B, what do you think? What is the surface charge density at B? So it's got to be Q, positive Q specifically, over 4 pi what? B squared. That's right, the surface charge density at B. Now, which one has a higher surface charge density? Yeah, it's more concentrated on the inside than the outside. That's also why the electric field is less. The outside of the sphere, the surface charge density is smaller. So that explains why we have this loss. Conductors and electric fields. I think I'm going to stop there because I'm pretty sure we're close to the bell ringing. Is that true?
Yes.